So when it comes to temperature, Kc and Kp as well are constants, but they're constants which depend on the temperature. They are temperature dependent. So if we change the temperature, we actually change the value of Kc. Let's take this equilibrium here. This is an endothermic reaction, okay? And let's think of it like this. So if we take this reaction and we write an expression for Kc and Kp, then you'll see that we've got essentially the same expression. We know that if we have an endothermic reaction and I increase the temperature, then that's going to favour the forward rate of reaction, and we're going to end up with more products than we had before. The equilibrium position is shifting to the right. And that means that at the end of that change, we are going to get an increase in temperature. The equilibrium will shift right, and therefore we're going to get an increase in the products and a decrease in the reactants. And this is a permanent change. As long as we maintain this temperature, we will continue with this new ratio of products to reactants. And so therefore, when we raise the temperature of an endothermic reaction, we actually find that Kc and Kp change at this higher temperature to be increased themselves. Now, if I was to cool it down again, and I was to take it back to the original temperature, and allow it to get back to that, then we would find that it would go back to the original Kc. But at the higher temperature, as long as I stay at the higher temperature, we will find that the value of Kp and Kc is increased for an endothermic reaction. Now, for an exothermic reaction, it's slightly different. If we take this exothermic reaction, again, Kc and Kp are there. If we have an exothermic reaction, we raise the temperature, we're actually going to shift the equilibrium to the left, because the endothermic pathway, the reverse pathway, is favoured. The reaction rate backwards is going to be faster than the reaction rate forwards. And again, if we raise the temperature, we're going to shift that equilibrium, and it's going to be a permanent shift, which is going to remain as long as we have that temperature. So this time we're going to have an increase in the number of reactants and a decrease in the number of products, and therefore we're going to end up with a value of Kc and Kp which is decreased. So here's a table of some Kc values at different temperatures. Let's look at two reactions here. We've got the reaction of hydrogen and chlorine, which is in equilibrium. You can see that the equilibrium value at 300 K, you can see that the equilibrium position lies well over to the right. This is pretty much a forwards reaction at room temperature, and you can see that actually as we raise the temperature, you can see that the value of Kc is decreasing. So if the value of Kc is decreasing, then that means we have less product on the top of our fraction of our Kc expression, and therefore, if that's true, then the equilibrium must be shifting to the left. And then, therefore, that must be an exothermic reaction because our Kc is decreasing with rising temperature, and also we can see that therefore we're going to, by heating it up, we're going to get more reactant back. The reverse reaction is favoured. With our second one, chlorine forming chlorine radicals, that's in an equilibrium. You can see that at even 1000 K, that's shifted over to the left. It's it's going to happen, but it's not going to produce an awful lot of chlorine radicals. But you can see that if we raise the temperature to 1200 Kelvin, then we're going to change the equilibrium constant to 1.7 times 10 to the minus 5. So that's going to get larger. So if we have an increase in Kc, then that means as we raise the temperature, then we're going to get more product. And if that's the case, then we're going to end up with an endothermic reaction. So we can tell from these Kc values whether a reaction is endothermic or exothermic.